The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Hi, our lecture today involves the backbone of calculus, namely the concept of limit. And perhaps no place in the history of mathematics is there a more subtle topic than this particular one. I'm reminded of the anecdote of the professor who was staring quite intently, philosophically, in his home when his wife asked, "What are you contemplating?" And he said, "It's amazing how electricity works." And the wife said, "Well, what's so amazing about that? All you have to do is flick the switch." And this somehow or other is exactly the predicament that the limit concept falls into. From the point of view of computation, it seems that what comes naturally, 99% of the time, gives us the right answer. But that unfortunately, the 1% of the time turns up almost all the time in differential calculus. For this reason, what we will do is introduce the concept of limit through the eyes of differential calculus, and we shall call our lecture today Derivatives and Limits. And what we shall do is go back to our old friend who makes an appearance in almost all of our lectures so far, the case of the freely falling object. A ball is dropped, it falls freely in a vacuum, and the distance s that it falls in feet at the end of t seconds is given by s equals 16t squared. The question that we would like to raise is, how fast is the ball falling when t equals 1? In other words, notice that the ball is covering a different distance here as it falls. What we want to know is at the instant that the time is 1. And by the way, don't confuse the speed with the displacement. We know that when the time is 1, the object has fallen a distance of 16 feet. When the time is 1, the object has fallen 16 feet. What we want to know is how fast is it falling at that particular point. Now keep in mind that mathematics, being a logical subject, proceeds from the idea of trying to study the unfamiliar in terms of the familiar. What we are familiar with is the concept known as average rate of speed. So what we will do is duck the main question temporarily and proceed to a different question. What we shall ask is, what is the average speed of the ball during the time interval from t equals 1 to t equals 2? And we all know how to solve this problem from our pre-calculus courses. Namely, we compute where the ball is when t is 2. We compute where the ball was when t is 1. The difference between these two distances is the distance that the ball has fallen during this time interval, and we then divide by the time interval. And the distance divided by the time is precisely the definition of average rate of speed. In other words, during the time interval from t equals 1 to t equals 2, the ball falls at an average speed of 48 feet per second. Again, in terms of our diagram, you see at t equals 1, the object is over here. At t equals 2, the object is over here. It's fallen 64 feet. And so we compute the average speed by taking the total distance and dividing by the time that it took. Now, again, what we have done is found the right answer, but to the wrong question. The question was not what was the average rate of speed from t equals 1 to t equals 2. It was what is the speed at the instant t equals 1. And we sense that between t equals 1 and t equals 2, an awful lot can happen, and that therefore our average speed need not be a good approximation for the instantaneous speed. What we do next, you see, is we say, okay, let's do something a little bit differently. Let's now compute the average speed, but not from t equals 1 to t equals 2, but rather from t equals 1 to t equals 1.1. And computationally, we mimic the same procedure as before. We compute s when t is 1.1. We compute s when t is 1. By the way, the only difference is that it's a little bit tougher to square 1.1 and multiply that by 16 than it was to square 2 and multiply that by 16. The arithmetic gets slightly messier, if you want to call it that. But the concept stays the same. We find the total distance traveled during the time interval, we divide by the length of the time interval, and that quotient, by definition, is the average rate of speed. Again, in terms of our diagram, at t equals 1, the object has fallen 16 feet. I'll distort this so that we can see what's happening here. At t equals 1.1, the object has fallen 19.36 feet. And now we compute the average speed from here to here in the usual high school way. Now again, the same question arises as before. Namely, this is still an average speed. We wanted an instantaneous speed. And our comeback is to say, look, we at least suspect intuitively that between 1 and 1.1, we will hopefully get a better idea as to what's happening at exactly 1 than we did on the bigger interval from 1 to 2. In other words, whereas we don't believe that 33.6 is the answer to our original question, we do believe that 33.6 is probably a better approximation to the answer to our original question than the answer 48 feet per second that was obtained over the larger interval. What the mathematician does next is he says, well, let's stop playing games. Let's not go between 1 and 1.1 or 1 and 1.01. Why don't we go between 1 and 1 plus h, where h is any non-zero amount? In other words, let's find the average speed from t equals 1 to t equals 1 plus h. And then what we'll do is we will investigate to see what happens when h gets very, very small. Well, again, we mimic exactly our procedure of before. We feed in t equals 1 plus h and compute s, which of course is 16 times 1 plus h squared. Then we subtract off the distance that the particle had fallen when t is 1. That's 16 feet. We divide by the length of the time interval. Well, between 1 and 1 plus h, the time interval is h. We simplify algebraically, and we wind up with this particular expression, 32h plus 16h squared over h. And now we come to the crux of what limits and derivatives and instantaneous rate of speeds are all about. If you recall, it's quite tempting to look at this thing and say, aha, I'll cancel an h from both the numerator and the denominator. And that will leave me 32 plus 16h. And notice, though, the very important thing, that as we mentioned in previous lectures, since you cannot divide by 0, it is crucial at this stage that we emphasize that h is not equal to 0. Now, of course, this is not a difficult rationalization to make. Namely, in terms of our physical situation, we wouldn't want to compute an average rate of speed over a time interval during which no time transpired. And if we let h be 0, obviously from 1 to 1 plus h, no time transpires. But the key statement is, and we'll come back to exploit this not only for this lecture, but for the next one too, is to exploit the idea that in our entire discussion, it was crucial that h not be allowed to equal 0. In other words, the average speed between 1 and 1 plus h is 32 plus 16h. Now again, without trying to be rigorous, observe that our senses tell us that as h gets as close to 0 as we want, without ever being allowed to get there, 16h gets as close to 0 as we want also, and hence 32 plus 16h apparently gets as close to 32 as we wish. In other words, it appears that the speed is 32 feet per second when t equals 1. And to reuse the vernacular, what we're saying is we compute the average rate of speed, see, s of 1 plus h minus s of 1 over h, and see what happens to that as h approaches 0. And in our particular case, notice that this simply means what? We came down to 32 plus 16h over here, and then as h got arbitrarily small, we became suspicious and believed that as h became arbitrarily small, 32 plus 16h became 32. And I'm saying that in great detail because this is not quite nearly as harmless as it may seem. There is a great deal of difficulty involved in just saying as h gets close to 0, 32 plus 16h gets close to 32. Well, there's no difficulty in saying it. There's difficulty that comes up in trying to show what this means precisely, as we shall see in just a little while. By the way, it's rather easy to generalize this result. Namely, you may have noticed in our presentation there was nothing sacred about asking what was the speed when t equals 1. One could just as easily have chosen any other time t, say t sub 1, and asked what was the speed between t1 and t1 plus h. We could have done exactly the same computation. In fact, notice down here, when we do this computation, the answer 32t1 plus 16h becomes precisely 32 plus 16h when t1 happens to be 1. In other words, this result here is the generalization of our previous result that had us work with the limit of 32 plus 16h. At any rate, by this approach, it becomes clear then, if the equation of motion, the distance versus the time, is given by s equals 16t squared, then at time t equals t1, the instantaneous speed appears to be 32 times t1. And in fact, since t1 happens to be any arbitrary time that we choose, it is customary to drop the subscript and simply say what? At any time t, our freely falling body in this case will have a speed given by 32t. And many of us will remember, as this is a revisited course, that this is precisely the recipe that turns out when one talks about bringing down the exponent and replacing it by 1 less. 16 times 2 is 32, and t to a power 1 less than 2 is just t to the first power, or t. But notice now, no recipes involved here, just a question of intuitively defining instantaneous speed in terms of being a limit of average speeds. Now, in order that we don't become hypocrites in what we're doing, recall also that we have spent an entire lecture talking about the value of analytic geometry in the study of calculus, the idea that a picture is worth 1,000 words. So what we would like to do now is to revisit our previous discussion in terms of a graph. You see, suppose we have a curve y equals f of x. And I've drawn the curve over on the side over here. We'll make more reference to it later as we go along. But what does it mean if I now mechanically compute f of x1 plus delta x minus f of x1 over delta x? And by the way, again, notice just a question of symbolism. Delta x happens to be the conventional symbol that one uses in the analytic geometry approach, where we were using h before. But this is simply a question of notation. Well, the idea is this. Observe that if we go to the graph, f of x1 plus delta x is this particular height. On the other hand, this height is f of x1. Consequently, our numerator is just this distance here. And our denominator, which is delta x, is just this distance here. And therefore, what we have done in our quotient is we have found the slope of the straight line that joins P to Q. And here then is why the question of straight line becomes so important in the study of differential calculus, that what is average speed in terms of analysis becomes the slope of a straight line in terms of geometry. And the idea, you see, is that this gives me the average speed between of the straight line that joins the average rise of the straight line that joins P to Q. And by the way, this is quite deceptive, as any average is. You know, it's like the man who sat with his feet in the oven and an ice pack on his head, and when somebody said, "How do you feel?" he said, "On the average, pretty good." You see, the same thing is happening over here. Notice if I had taken a completely different curve, a curve which looked nothing at all like my original curve, only that it also passed through the points P and Q, notice that even though these two curves are quite different, the average rise from P to Q is the same for both curves. In other words, when one deals with the average, one is not too concerned with how one got from the first point to the second. You see, this is the problem with average rate of speed. In fact, the bigger a time interval we work over, the more danger there is that the average rate of speed will not coincide intuitively with what we would like to believe that the instantaneous rate of speed is. And you see, that's exactly what this idea here means. What we do to define the derivative, the instantaneous rise at x equals x1, is we take this quotient and investigate what happens to it as delta x is allowed to get arbitrarily close to 0. But let's emphasize this again. Delta x is not allowed to equal 0. You see, it's over a smaller and smaller interval. And you see what's happening here geometrically? To let delta x get smaller and smaller means that for a given x1, you are holding p fixed and allowing q to move in closer and closer to p. And what we are saying is that when q assumes this position, let's call it q sub 1, the slope of the line that joins p to q1 looks a lot more like the slope of the line that will be tangent to the curve at the point p. And for this reason, what is instantaneous rate of speed when we're talking about functions becomes slopes of curves at a given point when we are talking about curves. You see that the tangent line to a curve is viewed as being the limiting position of a chord drawn from a point P to a point Q. Now, at any rate, this will be emphasized in the text. It will be emphasized in our exercises. The major issue now is, what did we really do when it came time to compute this little gadget? In other words, when we talked about the limit of f of x as x approached a, how did we compute this? The danger is, and this is why I've underlined a question mark here, the intuitive approach is to say something like, let's just replace x by a in here. In other words, let the limit of f of x as x approaches a be f of a. In fact, this is what we did with our 32 plus 16h. In a way, what we did was with 32 plus 16h. Do you remember what we did? We said, let's let h get arbitrarily close to 0. And in our minds, we let h equal 0. 16h was then 0. And then 32 plus 16h was then 32. But what we had done is somehow or other, if our intuition is correct, we had arrived at the correct answer, but for wrong reasons. Because you see, in this expression, it is mandatory, as we've outlined this, is that x never be allowed to equal a. Well, you say, who cares whether you allow it or you don't? Aren't we going to get the same answer? And just to give you a quickie, one that we talked about in our introductory lecture, consider the function f of x to be x squared minus 9 over x minus 3. And let's evaluate what this limit is as x approaches 3. If we were to blindly assume that all we have to do is replace x by a, that would mean what here? Replace x by 3. Notice that what we got is what? 3 squared, which is 9, minus 9, which is 0, over 3 minus 3, which is also 0. In other words, if in the expression x squared minus 9 over x minus 3, you replace x by 3, you do get 0 over 0. Unfortunately, or perhaps fortunately, somehow or other, this definition is supposed to incorporate the fact that you never allow x to equal 3. See, the way we got 0 over 0 was we violated what the intuitive meaning of limit was. We wound up with this 0 over 0 mess by allowing x to equal the one value it is not allowed to equal here. To see what happened more anatomically in this particular problem, let's go back to our old friend of cancellation again. We observe that x squared minus 9 can be written as x plus 3 times x minus 3. And then we divide by x minus 3. And here's where the main problem seems to come up. One automatically, somehow or other, gets into the habit of canceling these things out. But the point is, since we have already agreed that you cannot divide by 0, the idea then becomes that the only time this is permissible is when x is unequal to 3. In fact, to have been more precise, what we should have said was not that x squared minus 9 over x minus 3 equals x plus 3, but rather x squared minus 9 over x minus 3 equals x plus 3 unless x equals 3. And by the way, I should add here, what? That if x equals 3, then x squared minus 9 over x minus 3 is undefined. You see, that's what we called 0 over 0, undefined, indeterminate. See? But here's what bails us out. As soon as we say the limit as x approaches 3, what are we assuming? We're assuming that x can be any value at all except 3. And the interesting point now becomes that as long as x is anything but 3, the only time you could tell these two expressions apart was when x happened to equal 3. So if you now say we won't allow x to equal 3, then it is true that whereas the bracketed expression by itself is not equal to the parenthetical expression by itself, the limit as x approaches 3 of these two expressions are equal. And in fact, one becomes tempted to say, what in this case? Oh, here it's quite easy to see that as x approaches 3, x plus 3 is equal to 6. And let me put a question mark here also, because it certainly is true that if you replace x by 3, this will be 6. But this says don't replace x by 3. Now, before, when we replaced x by 3, we got into trouble, so we said we can't do that. Now we replace x by 3, we get an answer that we like, and now there's the danger that we'll say, okay, we won't allow this to be done unless we like the result. And of course, this gives you a highly subjective subject matter here. You see, the point is that somehow or other, we must come up with a more objective criteria for distinguishing what limits are. And by the way, for the Pollyanna who has the intuitive feeling for saying things like, well, look it, this may give you trouble if you wind up with 0 over 0, but what is the likelihood that given f of x at random and a at random, that the limit of f of x as x approaches a is going to be 0 over 0 if you're careless? And the answer is that the probability is quite small, except in calculus, in which case every time you take a derivative, every time, you are going to wind up with 0 over 0. This is why we said earlier that differential calculus has been referred to as the study of 0 over 0. You see, the whole point is, let's go back now to our basic definition of average rate of change of f of x1 plus delta x minus f of x1 over delta x. And I guess when you're writing in black, you have to use white for emphasis, so we'll use this. Notice that every time you let delta x equal 0, you are going to wind up with what? F of x1 minus f of x1, which is 0, over delta x, which is 0. In other words, you are going to get 0 over 0 if you believe that all this means is to replace delta x by 0. You see, and the point is, this is not the definition of this, and this is why you don't wind up with this particular thing. Well, I've spent enough time, I think, trying to give a picture as to what limits mean intuitively. Now what I'd like to do is to devote the remainder of this lecture, plus our next one, to investigating more stringently what limit means in a way that is unambiguous. And you know, it's like everything else in this world. When you want to get something that is ironclad, you don't get something for nothing. To get an ironclad expression that doesn't lend itself to misinterpretation usually involves a rigorous enough language that scares off the uninitiated, sort of like a legal document. The chances are, if you're not a trained lawyer and the document is simple enough for you to understand, it must have thousands of loopholes in it. But that same rigorous language that makes it almost impossible for the layman to understand what's happening is precisely the language that the lawyer needs to make the document well defined to him, hopefully. Well, with that as a background, let's now try to give a more rigorous definition of limit. And let's try to do it in such a way that not only will the definition be rigorous, but it will agree to the best of our ability with what we intuitively believe a limit should mean. Now, what I want to do here is scare you a little bit. The reason I want to scare you a little bit is I want to show you once and for all how in many cases what appears to be ominous mathematical notation is simply a rigorous way of saying something which was quite intuitive pictorially to do. The mathematical definition of limit is the following. The limit of f of x as x approaches a equals L means, and get this, given epsilon greater than 0, we can find delta greater than 0, such that when the absolute value of x minus a is less than delta but greater than 0, then the absolute value of f of x minus L is less than epsilon. Now, doesn't that kind of turn you on? See, this is the whole problem. I will now cut you in sort of on the trade secret that makes this thing very, very readable. First of all, to say that you want to get arbitrarily close in value, you want f of x to be arbitrarily close to L, another way of saying that is what? You specify any tolerance limit whatsoever, which we call epsilon. And I can make f of x get to within epsilon of L just by choosing x sufficiently close to a. And by the way, again, in terms of geometry, that's all the absolute value of a difference means. The absolute value of x minus a simply means what? The distance between x and a. All this says is what? I can make f of x fall within epsilon of L by finding a delta such that x is within delta of a. And by the way, this little tidbit over here is simply a fancy way of saying that you're not letting x equal a. You see, the only way the absolute value of a number can be 0 is if the number itself is 0. The only way this could be 0 is if x equals a. So by saying this little tidbit over here, that this is greater than 0, that's our fancy way of saying that we are not going to allow x to equal a. Now, again, whereas this may sound a little bit simpler than the original definition, let's see how much easier the picture makes it. Let's go to a graph of y equals f of x. And in my diagram here, here is a and here is L. And what I'm saying is, I intuitively suspect, let me write down what I suspect. I suspect that the limit of f of x as x approaches a is L in this case. Namely, I suspect that as x gets closer and closer to a, no matter which side you come in on, see? That's why we use absolute value. It makes no difference whether it's positive or negative. As x gets in tighter and tighter on a, I suspect that I can make f of x come arbitrarily equal to L. In other words, if x is close enough to a, f of x, it seems, will be close to L. And by the way, to complete this problem geometrically, pick your epsilon. Let's say that epsilon is this wide. Then since epsilon is positive, this will be called L plus epsilon. This will be called L minus epsilon. Now what we do is we come over to the curve here. All right? Hopefully these will look like horizontal lines to you. When I get down to here, I then project down vertical lines to meet the x-axis. And now all I'm saying, and I think this is fairly intuitively clear, is what? That if x is this close to a, f of x will be within these tolerance limits of L. In other words, for any value of x in here, see, for this neighborhood of a, every input has its output come within epsilon of L. By the way, just one brief note here, something that we'll have to come back to in more detail. In fact, I'll do that in our next example. Notice here how important it was that our curve was not single valued, but one-to-one. In other words, suppose our curve had doubled back, say, something like this. Notice then, when you try to project over to the curve from L plus epsilon, you don't know whether to stop at this point or at this point. You see, in other words, notice that there is another point down here which has the same L plus epsilon value. In other words, whenever our function is not one-to-one, there is going to be a problem when we work analytically of being able to solve algebraic equations and trying to distinguish this point of intersection from this point. You see, if we made a mistake and bypassed this point and came all the way over to here and thought that this was our tolerance limit, we would be in a great deal of difficulty because, you see, for example, for this value of x, its f of x value projects up here, which is outside of the tolerance limits that are given. You see, many things which are self-evident from a picture are not nearly so self-evident analytically, to which we then raise the question, why use analysis at all? Let's just use pictures. And again, the answer is, in this case, we can get away with it, but in more complicated situations where either we can't draw the diagram because it's too complicated, or because we have several variables and we get into a dimension problem, the point is that sometimes we have no recourse other than the analysis. Let me give you an exercise that we'll do in terms of putting the geometry and the analysis side by side. Let's look at the expression, the limit of x squared minus 2x as x approaches 3. Now, of course, we don't want x to equal 3 here, but let's cheat again and see what this thing means. Our intuition tells us that when x is 3, x squared is 9, 2x is 6, so 9 minus 6 is 3, and we would suspect that the limit here should be 3. Now, to see what this means, let's draw a little diagram. The graph y equals x squared minus 2x crosses the x-axis at 0 and 2. It has its low point at the point 1 comma minus 1. See, we can sketch these curves. It's a parabola. And now what we're saying is it true that when x gets very close to 3, is it true that when x gets very close to 3, that f of x gets very close to 3? And the answer is, from the diagram, it appears very obvious that this is the case. In fact, here's that example of non-single valued again. If you call this thing L, and you now pick tolerance limits, which we'll call L plus epsilon and L minus epsilon, and now you want to see what interval you need on the x-axis, notice that in this particular diagram, you will get two intervals, one of which surrounds the value x equals minus 1, and the other of which surrounds the x value x equals 3. In other words, both when x is minus 1 and x is 3, x squared minus 2x will equal 3. See? At any rate, leaving the diagram as an aid, let's see what our Epsilon-Delta definition says and how we handle this stuff algebraically and how we correlate the algebra with the geometry. Given epsilon greater than 0, what must I do? I must find a delta greater than 0 such that when, and I'm going to read this colloquially, I'll write it formally, but read it colloquially, such that whenever x is within delta of 3, but not equal to 3, then x squared minus 2x will be within epsilon of 3. Now here's the whole point. We know algebraically how to handle absolute values. Namely, the absolute value of x squared minus 2x minus 3 being less than epsilon is the same as saying that x squared minus 2x minus 3 itself must be between epsilon and minus epsilon. Now again, we rewrite things in fancy ways if we wish. There are other ways of doing this. I call this completing the square. Well, people for 2,000 years have called this completing the square. Namely, I rewrite minus 3 as 1 minus 4, so that x squared minus 2x plus 1 can be factored as x minus 1 squared. I'm now down to this form here. Then I add 4 to all sides of my inequality and have that x minus 1 squared is between 4 plus epsilon and 4 minus epsilon. Some fairly elementary algebra of inequalities here. Now here's the key point. Remember in my diagram I said to you, how do we know whether we're near 3 or near minus 1? How do we distinguish when we draw the lines to the curve what neighborhood we want? And notice that all we're saying is that if x is near 3, that means what? X is close to 3? If x is reasonably close to 3, then x minus 1 is going to be reasonably close to 2, and hence be positive. Point is that as long as you're dealing with positive numbers over here, see if epsilon is sufficiently small, these will then all be positive numbers. For positive numbers, if the squares obey a certain inequality, the square roots will obey the same inequality, as we have emphasized in one of our exercises. In other words, from here, we can now say this. And from this, we can now conclude that if you want x squared minus 2x to be with an epsilon of 3, x itself is going to have to be between 1 plus the square root of 4 plus epsilon, and 1 plus the square root of 4 minus epsilon. And by the way, this is quite rigorous, but I don't think it turns you on. I don't think there's any picture that you associate with this. And so what I thought I'd like to do for our next little thing is to come back to our diagram here and show you what this really means. Namely, notice that if epsilon is a small positive number, let's take a look at this again. If epsilon is a small positive number, this is slightly less than 4. Therefore, the square root is slightly less than 2. Therefore, this number will be slightly less than 3. On the other hand, 4 plus epsilon is slightly more than 4, so its square root will be slightly more than 2, and therefore 1 plus that square root will be slightly more than 3. And what these two numbers, as abstract as they look like, correspond to is nothing more than this. Coming back to our diagram and choosing an epsilon, and coming over to the curve like this, and projecting down like this. All we're saying is, see, what are we saying pictorially? That for f of x to be within epsilon of L, x itself has to be in this range here. And all this says is that if this very simple point to compute, just by projecting down like this, its rigorous name would be 1 plus the square root of 4 minus epsilon. That's this number over here. And the furthest point, namely this point here, which again, in terms of the picture, is very easy to find, that point corresponds to 1 plus the square root of 4 plus epsilon. And again, notice, in terms of the algebra, I need no recourse to a picture, but in terms of the picture, I get a heck of a good feeling as to what these abstract symbols are telling me. Well, let's continue on with the solution of this exercise. You see, we didn't want to find where x was. We wanted to see where x minus 3 had to be. In other words, we're trying to find the delta. We know that x minus 3 is between these two extremes here. Consequently, and here's the place we have to be a little bit careful here, this, of course, is a positive number because this is more than 2. This, on the other hand, is a negative number because you see 4 minus epsilon is less than 4, so its square root is less than 2. You see, so if I subtract 2 from it, it's a negative number. And since delta has to be positive, if this thing is negative, 2 minus the square root of 4 minus epsilon will be positive. So what I do is, to solve this problem, is I simply choose delta to be the minimum of these two numbers. And then, by definition, what do I have? That when the absolute value of x minus 3 is less than delta, and at the same time, this is crucial, greater than 0, in other words, we never let x equal 3, for this choice of delta, by how we work backwards, this will come out to be less than epsilon. And that is exactly what you mean by our formal definition of saying that the limit of x squared minus 2x as x approaches 3, in this case, equals 3. For someone who wants more concrete evidence, I think all one has to do is, for example, take a number like 1 plus the square root of 4 plus epsilon. That is the widest point on our interval. And actually plug that in for x. And go through this computation of squaring 1 plus the square root of 4 plus epsilon. Subtract twice 1 plus the square root of 4 plus epsilon. Carry out that computation, and you get what? 3 plus epsilon. That using the upper extreme, you wind up with what? In excess of 3 by epsilon, which, by the way, is exactly what's supposed to happen. In fact, I hope this doesn't give you an eyesore. I will pull down the top board again to show you also what these two distances mean and what this means. You see, all these two numbers mean is the following, and I'll pull this down just far enough to see it. That these two numbers were the widths from this endpoint to 3 on the one extreme, and from this endpoint to 3 on the other extreme. In other words, those two numbers that we took the minimum of were the half-width intervals that surrounded 3. You see, the problem, as we mentioned before, is that even though epsilon and minus epsilon are symmetric with respect to L, when you translate over to the curve, because this curve is not a straight line, when you project down, these two widths will not be equal. And by picking the minimum of these two widths, you guarantee that you have locked yourself inside the required area. You see, that's all this particular thing means. Now, the trouble is that one might now get the idea that there are no shorter ways of doing the same problem. You see, I showed you a rigorous way. There was no law that said we had to find the biggest delta. In other words, if delta equals a half will work, in other words, if you're within a half of 3, something's going to happen, then certainly any smaller number will work just as well. Right? In other words, I can get estimates. Let me show you what I mean by that. See, another way of tackling how to make x squared minus 2x minus 3 smaller than epsilon is to use our properties of absolute values and to factor this. In other words, we know that x squared minus 2x minus 3 is x minus 3 times x plus 1. We know that the absolute value of a product is the product of the absolute values. So these two things here are synonyms. Then we know that near x equals 3, which we're interested in here, x plus 1 is near 4. Well, what we mean more rigorously is this. Choose an epsilon. And if the absolute value of x minus 3 is less than epsilon, in other words, if x minus 3 is less than epsilon but greater than minus epsilon, then by adding on 4 to all three sides of the inequality here, we see that x plus 1 is less than 4 plus epsilon but greater than 4 minus epsilon. Now you see, if we simply assume that epsilon is less than 1 in magnitude, see, if epsilon, an absolute value, if the size of epsilon is less than 1, then certainly this is less than 5 and this is greater than 3. Now, of course, somebody may say to us, but what if epsilon is more than 1? Well, obviously, if a guy says, make this thing within 10, and I can make it within 1, certainly within 10 is within 1. I can always pick this smaller number. I mean, it's like that nonsense of the fellow asking for an ice cream cone, and the waitress said, what flavor? And he said, anything except chocolate. And she said, I'm all out of chocolate. Will you take anything except vanilla? I mean, the idea is that if somebody says, make this less than 15, if you've made it less than 10, in particular, you've made it less than 15. And so all we do over here, you see, is something like this. We say, look, if we want to make this number here very small, we know that this number here is less than 5. We know that epsilon over 5 is a positive number if epsilon is small. So why don't we just pick the absolute value of x minus 3 to be less than epsilon over 5? In fact, that's what this delta will be in that case. In other words, if the absolute value of x minus 3 is within epsilon over 5 of 3, see, if x is within epsilon over 5 of 3, notice what this product becomes. This is less than epsilon over 5. This we know from before is less than 5, and therefore this product is less than epsilon. In other words, we have exhibited the delta such that when this happens, the absolute value of what we want to make less than epsilon indeed becomes less than epsilon. Now, because I recognize that this is a hard topic, you will notice in the reading assignments that these problems are covered in great detail. Everything that I've said in the lesson so far is repeated in great computational depth in our learning exercises. The point is that even if I can make the epsilons and deltas seem a little bit more meaningful for you than by the formal definition, notice that it's simple only in comparison to what we had before, that it's still very, very difficult. The beauty of calculus is that in many cases we do not have to know what delta looks like for a given epsilon. What we shall do, therefore, in our next lecture is to develop recipes that will allow us to get the answers to these limit problems without having to go through this genuinely difficult problem of finding a given delta to match a given epsilon. Though we must admit, in real life, in many cases where you're making approximations, we will want to know what the tolerance limits are. I am not belittling the epsilon-delta approach. All I'm saying is that in certain problems you do not need the epsilon-delta approach to get nice results. And that will be the topic of our next lecture. So until next time, goodbye.
Funding for the publication of this video was provided by the Gabriella and Paul Rosenbaum Foundation. Help OCW continue to provide free and open access to MIT courses by making a donation at ocw.mit.edu/donate.